Hi, this is Mark with Cynthia and Shelley from the Center for Math and Teaching. If you don't know us or our work, we're happy to meet you. We're a nonprofit and we develop middle school mathematics curriculum and resources, and we support teachers in using them through professional development. We worked together in the math department at UCLA for about a decade, and then about 11 years ago, we left the university to form CMAT. Today, our focus is whole number multiplication strategies, and mostly it's targeted to working with students who have been exposed to this topic before and are still struggling. Before we start, I want to tell you my little multiplication story. Oftentimes when I'm out in the world with people and they know that I'm a math educator, they will take it upon themselves to complain to me about what their students are doing in their math classes and how Common Core has changed everything. And why don't teachers just teach them the rules and the facts and the algorithms? And so rather than get into that discussion with them, I first asked them to calculate 3 times 17 mentally. And so there might be 3, 4, 5, 6, 7 people, and invariably we hear about 2, 3, sometimes 4 different ways that they do this calculation. So, and you might be thinking about how you're doing it right now. After people share their different ways of doing it, it sort of springboards into a discussion where I explain to them that we're really just trying to help younger children make sense of the mathematics. The goals are, of course, to get to the algorithm, but how you get there is a real important journey. And so when we're teaching students number sense at younger ages, we are helping them get to their final goals. Here you see today's agenda. And remember, the strategies are pitched to learners who may not have mastered the content the first time or the first few times they saw it, but it's based on strategies proven to be effective with younger students as well. Let's start with single-digit strategies. It's very common to teach breaking numbers apart. This helps students create their own meaning for the products they're working with. And we know that being able to break numbers apart and then put them back together is a sign of flexibility with numbers and good number sense. Let's take a look at June's strategy. And think about what she did. Now let's take a look at Wade's strategy. Think about what Wade did. Now, when I look at it, to me, they both broke numbers apart. They might have some kind of intuitive knowledge about the commutative property. June knows that 8 times 6 is 5 eighths and another 1 8. Wade knows that 8 times 6 is 4 sixes, and then he can double that to get 8 sixes. So they're showing flexibility in thinking. And to me, these kinds of situations really lend themselves very nicely to number talks or math talks, if you're familiar with those. If you've worked with teachers for a long time like we have, we hear this comment all the time. And my first reaction is, really? They don't know any of them? Cynthia actually tells a story about her experiences with her students. Will you jump in here, Cynthia?
Sure, I'd be happy to. So when I taught middle school, which I did for 13 years, I had many students who'd say, I just don't know my times tables. General blanket statement. So I gave them a blank 10 by 10 grid, and I said, fill in all of the ones that you know. And most of them, once they started filling them in, obviously the ones, the twos, even the threes filled in pretty easily, the fives filled in, the tens filled in, and then they were kind of able to work from there. And when they got to the end of it, they really realized that there was probably about 3, 4, 5 that they didn't know. The 6 times 7, 7 times 8, and those types of problems that you're sharing right now on your screen were the ones that seemed to really hold them up. So it was eye-opening to them, totally changed their outlook, made them feel a lot more confident that I really do know most of them and I could figure out a way to solve the ones I don't.
Okay, thanks.
Sure.
So what you're saying when it comes down to it, more students probably know more of the times tables oftentimes than we give them credit for. Of course, students are everywhere, all over the map, but it's probably mostly these difficult products that that are the ones that are toughest to remember. Um, Shelley, you talked about some strategies that you used with some of your students that struggled.
Yeah, when I was teaching, I often had students that didn't know their facts. And like Cynthia, we determined which facts were problematic. But then I asked the students to write all the ones they didn't know in the margin of their paper every day when they would come to class. And sometimes they would write the whole fact, and sometimes they figured out that they could just write a skip counting list and that would be sufficient. But this made it possible for them to work without the facts slowing them down on the other work we were doing for the day. After writing them day after day, their list became shorter and shorter until the multiplication fact issue was resolved for them.
Thanks, Shelley. So as with filling any gaps in student knowledge, the intervention research tells us to chip away at it. As an example, if this is something that your students really need practice with, be strategic. Create short 5 to 10-minute routines that can be done daily or almost daily over a span of however long it takes, a couple of weeks, let's say. They can write things down in their margins, like you see here, and it might be done through number talks, like we've talked about before. And here we remind you that deriving or retrieving single-digit facts might be expanded pretty quickly into multiplying by multiples of 10, like you see some examples here. So let's take what we've looked at so far and move on to the area model. We're going to start with a rectangle that's 6 by 14. So each little square is 1 square unit of area. So the entire rectangle is 84 square units. Rectangles are a natural context for multiplication because they're visual and they connect number sense to geometry. And we know that the area of a rectangle is the product of its side lengths. Students may already know this, or they may benefit from some time with square tiles, building various smaller rectangles and connecting the side length value to the area value. And one of the great things about an area model is just like breaking numbers apart, students can do whatever helps them create meaning. So for this first example, the rectangle is cut in half as shown, creating 2 smaller, more manageable rectangles. Here are the side lengths of those rectangles, and this is the arithmetic that would be required to figure out the product. Here's a second way to cut the same rectangle in half. Here are the side lengths. And here's the arithmetic involved to find the product, which of course is going to be the same as before. And here's a third way to cut the exact same rectangle. And this time we're using place values strategically so that the 14 is broken up into 10s and 1s. And so this is the arithmetic involved. And I think that doing this makes it a little bit easier because for me, probably for a lot of your students, 6 times 10 and 6 times 4 are easier calculations. So the model might be a bit cumbersome doing it this way because it is to scale. But remember, we're talking about students who are struggling with their multiplication. And so they're probably not great at memorizing their facts. And more importantly, they've probably not created meaning for this operation. So they probably do need the visual to start with. To move students forward, we can use a generic area model. This example is a single times a double digit product where we break apart the 57 into 10s and 1s. It's not based on any particular scale. It takes the idea of an area model and acts as a structured recording device. So here we still have what before we thought of as side lengths, and the areas are now the partial products, and we can just add them up to get the final product. Here's a 2 by 2 multiplication where both numbers are broken into tens and ones. Here's the rectangle where we can do the side lengths again, if you will, and the areas again. And with these partial products, we can add the rows, or if we chose, we could add the columns, doesn't matter. And we're going to get that sum, which is the final product. And with this last example, we're going to do a 2 by 3 multiplication, showing that you can expand this as far as you want. Here we have numbers broken into hundreds, tens, and ones. This is the rectangle that goes with it. And we'll find all those partial products again and do a lot of addition in rows or in columns to get our final product. So this is a really nice transition from the scale area model to the generic area model. And it still helps students who are going to benefit from the visual and the structure. Now, you might be thinking that this is cumbersome as well, especially for larger values. And that's going to create the need for something different, something more efficient. So that being said, we want to move students as they show the readiness to do so. Here we're going to connect the generic area model to what we're calling an expanded multiplication procedure. Watch how these two things are connected. There's the 3 times 4 in both, the 3 times 60, the 20 times 4, and the 20 times 60. So the expanded procedure is not as compact as the standard algorithm, but it serves as a process that's more efficient possibly than the area model, but it maintains the integrity of the place value idea. So it makes a nice transition. Students are reminded that the 6 in 64 is in the tens place, and the 2 in 23 is in the tens place. Now we'll connect the expanded procedure to the standard algorithm, where before we did the 3 times 4 and the 3 times 60. In the standard algorithm, we still do the 3 times 4 and the 3 times 60, but it looks quite a bit different. It's much more compact. And in the expanded procedure where we did the 20 times 4 and the 20 times 60, we're doing the same thing in the standard algorithm, recognizing that we are in the tens place, and so we bring down the 0 to represent that. So this is the 20 times 4, and here's the 20 times 60. Same result, of course, but again, the standard algorithm is in a more compact form. And just so you know, what you saw here was taken from our MathLinks Essentials program. MathLinks Essentials is a modular program, and it's used for many purposes. It addresses the major work of middle school, plus some of upper elementary. Here are the 6 modules, and what you saw came from the number base 10 module. Here's our contact information again. We'd love to continue the conversation about whole number multiplication or any other topic that your students struggle with. Here's our website, and thanks for joining us.